Hi everyone, I'm Pengyu Qian, a fifth-year PhD student at Columbia Business School. Today I'm very excited to talk about a recent work joined with Itai Ashlagi, Jacob Leshno, and Amin Saberi. In this work, we study the waiting list mechanism, which is a very simple and widely used mechanism. Its applications include allocation of public housing, deceased donors' kidney, etc. In this work, we want to understand the performance, the allocative efficiency of such a simple mechanism. By drawing the interesting connection between stochastic price adaptation process under such mechanism and the stochastic gradient descent, we are able to obtain very novel and general results. Here is an overview of today's talk. So the object we are studying today is the waiting list mechanism. We also call it the queuing mechanism. This mechanism is very simple to implement and is very commonly used in applications. A key feature of this mechanism is that instead of using prices, it uses the waiting time to allocate the items. Because we're considering a stochastic environment, because of the stochasticity, the waiting time will randomly fluctuate over time. And we want to understand the performance of the waiting list mechanism in such an environment. Our key question is, what's the loss of allocation efficiency? We obtain three results that provides a pretty complete picture of its performance. The first result says that the loss of allocative efficiency under waiting list mechanism can be bounded by the size of price adjustment or the granularity of price. Interestingly, this result holds for a system of all sizes. And also, as the system size increases, the granularity of price diminishes to zero, which establishes the asymptotic allocative efficiency of the waiting list mechanism in large systems. In our second result, we show that our first result is essentially tight. We are able to construct several examples which thus achieve a loss of allocative efficiency in the size of the price adjustment. In the third result, we show that while there are bad cases, but when there are only a finite number of agent types and item types, and the dual prices in the competitive equilibrium is unique, the loss of allocative efficiency is actually negligible. We are able to obtain these results by using a novel methodology, linking the evolution of the queuing process with the stochastic gradient descent dynamics. We also use tools from linear programming duality and Leshno functions to obtain these results. There are many works in the literature that study the allocative efficiency in dynamic matching. A prevalent approach is to consider the underlying Markov chain of such a process, study its steady-state distribution explicitly, and obtain the performance guarantee from the steady state. As you can imagine, such an approach quickly becomes intractable when the number of agent types and item types grow large. In fact, when there are just three types of items and agents, the problem is already very difficult with this approach. However, in our work, because we use a completely different approach, we are able to deal with arbitrarily finitely many agent types and item types. We can even consider a continuum of agent types. Another related stream of literature is the study of the Tatonomon process. But the key difference is that in our work, the prices or the queue lengths are determined by the mechanism, while in the Tatonomon process, there's no mechanism and the price is chosen. Now let me introduce our model. So in our model, the items arrive according to a Poisson process with total rate 1. This is represented by the different shapes of objects here. So there are finitely many types, indexed by 1, 2, until j. And with probability mu j, the arriving item is of type j. The arrival rates and the distribution probability of item types are public information. So all the agents know that. The agents also arrive according to a Poisson process with total rate lambda. And the agent types are drawn IID from some distribution F. F can be very general, It can be distribution of atoms. It can also be a continuous distribution. And when an agent is matched to an item, it obtains utility. We assume the utility is quasi-linear. Suppose a type theta agent is assigned to a type J item. After waiting W periods of time in the system, it obtains a utility V theta J minus CW. Here, V theta J is the match value that depends on both the type of the agent, theta, and the type of the item J. And CW is the cost of waiting. W is the waiting time. If an agent leaves immediately, it will obtain a utility of 0. And we assume the match values are private information. So each agent only knows its own match values. Okay, so here is the model. We also made some regularity assumptions to prevent silly things from happening. In the interest of time, I'll skip that now. And the objective we are considering is the allocative efficiency. So allocative efficiency is just the average match value. Suppose the I agent has type theta I and is matched to an item eta I. The match value collected by this agent is V theta I eta I. If we take the average of the match values of all the arriving agents, this is the average match value, or the allocative efficiency. And we denote by W opt the optimal allocative efficiency that can be achieved by any dynamic matching. So here you may notice that in our objective, only the match values are involved, and it leaves out the waiting costs. While this assumption makes sense in some applications, for example, in public housing, the waiting cost is typically not viewed as a real cost, and people are more interested in the match values. Now let me introduce to you the very simple waiting list mechanism. So waiting list mechanism maintains a separate queue for each item. To make it concrete, you can think of a public housing allocation system. So the items are just different public housing projects. And there's a queue of people waiting for each project. So each queue are served in a first come, first served manner. And when the item arrives, if the corresponding queue is empty, the item will be discarded under this mechanism. And for an agent, if it decides to join the queue, it has to wait until being assigned. So there's no reneging. It cannot bulk in between. It can bulk when it joins the system. Otherwise, you will have to wait until the end. When the agent arrives, they can observe all the queue length for each item. They also know the arrival rates of the items because it's public information. They can join any queue or bulk immediately and leave unassigned. We assume the agents are rational, so they will be maximizing their expected utility, which is the match value for joining a queue minus the expected waiting time given the queue length. Because the agents know the queue length and the arrival rate of items, they know the distribution of waiting times as well. So they will join the queue that maximize expected utility. We denote the allocative efficiency under the queuing mechanism WQM. Before presenting the main result, let me introduce to you two key quantities in defining the result. First is the PJ of Q, which simply is the conditional waiting cost of joining QJ given its queue length QJ. So we use the letter P because this quantity plays the role of prices in such a mechanism. The expected waiting time plays the role of prices. Another very important quantity is this capital C, or the granularity of price. So this capital C is simply the maximum amount of change of the price if one additional agent joins a queue. This value is finite because the maximum possible queue length is finite. In the regularity assumptions, we assume that the match value is upper bounded. As a result, the queues cannot be too long. Otherwise, the waiting costs will outweigh the benefit and the agents will just simply not join. Okay? So here's our first main theorem. We show that the loss of allocative efficiency under the waiting list mechanism in very general system is bounded by this value on the right-hand side, which is lambda plus 1 over 2 lambda, which is a constant, times the granularity of price C. So recall lambda is the arrival rate of agents. Suppose the arrival rate of agents and items are the same, they are both 1, then this constant is just 1. So the key quantity here is C, which is the granularity of price. We can also look at this result in a slightly different perspective. Let's consider a sequence of economies where the distribution of agent types and item types stay fixed, but you speed up the arrival rate of agents and items by capital N. In this symptotic regime, the granularity of price C is inversely proportional to the system size N. So C is about 1 over N. As a result, as the system size N grows larger, the allocative efficiency diminishes to 0 at the rate 1 over N. Our second result is to show that is the upper bound tight? The answer is yes, because for any number of item types, we can construct economies where the loss of allocated efficiency is at least of order C, which is the granularity of price. Our third result complements our second result by saying that although there are bad cases, doesn't occur very often. For example, when there are just finitely many agent types and finitely many item types, then generically, which means with probability 1, the problem instance will have an allocative efficiency loss that's negligible as the system size grows larger. So its dependence on the system size is exponentially in N. Now let me explain how we obtain these results. To understand the result, we should first look at an offline benchmark of the average allocative efficiency that can be obtained for any policy. So this offline benchmark is just a one-shot matching problem. So on one hand, you have a continuum of item types. On the other hand, you have atoms of agent types. And you solve a matching problem where you try to maximize the match value. So we can show that this provides an upper bound for the allocative efficiency for any mechanism or policy. So this optimization problem is very complicated because it involves a continuum of decision variables. However, if you look at its dual, it looks actually very simple. So the dual is finitely dimensional problem. The dimension is the same as the number of item types. The dual variables adjust the dual prices for each item, represented by the P's here. And by the celebrated Monch-Kantorovich duality, we know that strong duality holds in this setting. So the optimal value of the dual problem indeed equals to the optimal value of the primal problem. So now the game reduces to finding the optimal dual price in the competitive equilibrium of the problem. Now let's look at the dynamics under the waiting list mechanism. So here is the grid of possible prices. Because the queue lengths can only take integer values, so the prices can only take values on the grid instead of on the continuum. Let's say P star is the optimal dual price in the competitive equilibrium, and PQT is the current price given the current queue length. Because the system has intrinsic randomness in the type of arriving agents and items, its transition is stochastic. It can move to different directions. And in the existing approach in the literature, people tend to solve for explicit steady state distribution of such a dynamics and understand its performance. However, it's very difficult in the general setting. But we have this interesting observation. If you look at the dynamics of the queue lengths closely, in one step, the expected change of the queue length is exactly a subgradient of the dual problem at the current dual price. So as a result, if you update the prices based on the waiting list mechanism, the queue length will be executing a stochastic gradient descent on the dual problem. So once you can show that the prices converge to the optimal price in the competitive equilibrium, you can establish the allocative efficiency laws of the waiting list mechanism. Now, let me explain when do we observe high loss in the allocative efficiency. So consider a simple case where there are just 2 item types and 2 agent types. Everything is perfectly balanced, so the arrival rates of all the items and agents are the same, right? And we assume allocating type 1 item to type 1 agent gives you a match value of 1. Allocating items and agents of different types gives you a match value of 1 minus epsilon. So the optimal matching will be just matching agents to the items of the same type. However, because the system is random, there's stochasticity, so the queue lengths will fluctuate over time. And when the queue lengths different are too large, people will start to join the wrong queue, incurring the loss in allocative efficiency. As you can imagine here, the queue lengths actually perform an unbiased reflective random walk. So with some probability, the queue length difference will be large. And we show that this probability is proportional to C, which is the granularity of prices. So for this example, the loss of allocative efficiency is at least as much as C. So these are the bad cases. Now let me wrap up. So in this work, we provide a rather complete analysis of the allocative efficiency in the simple waiting list mechanism. And we are able to obtain our results by drawing the connection to the stochastic gradient descent dynamics. We use Leshno functions to obtain these bounds. In the interest of time, I didn't cover the details here. And the random fluctuations in waiting times indeed cause an efficiency loss. The loss depends on the step size or the granularity of prices in these systems. And we have good efficiency when the offline prices or the due price in the competitive equilibrium are unique. That's pretty much it. Thank you.